académica del Seminario de Investigación de Operaciones. El día de hoy va a estar con nosotros el doctor Schütze, que es matemático y doctor en matemáticas aplicadas por la Universidad de Alemania en Paderborn. Y el día de hoy va a hablar sobre continuation methods for multi and many objective optimization problems.
Okay. Sí, muchas gracias por la invitación y por la introducción. Voy a empezar con dos malas noticias. Mala noticia número uno, voy a hablar en inglés. Well, that's very sorry. You heard already, if I would speak in Spanish, it would be bad for both of us. I lived in Mexico since some years, but still I would prefer to speak in English. I hope this is not a big problem for you. Then I have another news. The thing is that regarding the performance of my presentation, recently I got a surgery which was kind of grave. I think I'm better now, but I realize also today that I'm not back to normal. So it might be that, I will speak much slower than I normally do. My performance might not be the same. And it might be that after 30 minutes, in the worst case, I have to stop or whatever. I feel not so good. So please enjoy every slide I'm giving to you. Good. So today I'm going to talk about a very special topic. It's a so-called continuation methods for multi and many objective optimization problems. Also here I have to tell, Claudia invited me a long time ago, but I started preparing later, and later was my surgery. So I was not sure about the auditorium, and I thought that Claudia is in mathematical programming, which she is not, as you just told me. So I picked up a topic which is clearly in mathematical programming. Right. What I do is the research group. The name of my research group is called NEO, stands for Numerical Evolutionary Optimization, because I think it makes sense to hybridize numerical and evolutionary techniques in order to get the best, fast, and reliable algorithms. Right. But today I picked up a topic which is completely a mathematical programming, but which is for us a nice starting point for classical NEO. That is, we use this method now in a framework of numerical and evolutionary algorithms. But today I'm going only to talk about continuous multi and many objective optimization problems. Good. So the outline is as follows. I will introduce a bit to the topic, which is multi and many objective optimization. We will see mathematically multi and many objective optimization problems, they are the same, right? But from the practical point of view, they are completely different, which means they need different treatments for the effective application of such methods. And that's why we will divide multi and many objective optimization problems. And then, I'm here to make advertising, of course. I make advertising for my methods. And I think that I want to convince you that the Pareto tracer is a very nice tool, among others, of course, to treat multi-objective problems. And the Pareto Explorer is a nice framework or tool to compute these many objective optimization problems. And finally, I will end up with a real-world application which is related to industrial design of laundry systems. So let us start. Multi-objective optimization and many objective optimization is the task. What is this? So I assume that you're all familiar with classical optimization, right? Classical optimization is the optimization of one single objective. So you would like to have the fastest car, you would like to have the cheapest car, you would like to have the fanciest car, whatever that is, right? But if you look outside, you will not see the fastest car, you will not see the safest car, you will see compromises, because people ideally want to have both, or if there are three cases, three things. They want all. They want it fast and cheap and safe and so on, right? So this leads mathematically to a so-called multi-objective optimization problem. So instead of one objective, we have k objectives. And every of these objectives, fi, maps from the Rn, so we have n decision variables into the R. So the total thing, big F, I call it in the future, in the following, is mapping from the Rn, n decision variables into the Rk. So we have now k different objective functions the question is, what is an optimal thing? So this we have to do. So this slide, though its background is not my research, it's the one you have to understand. So please pay attention here, because if you don't understand this, the rest will be like not so interesting for you. So on the right-hand side, we see one example. There we see the red curve and the blue curve. So since I assume that you know what single objective optimization is, you know already where the solution is for the red curve. That would be here, right? This is the best one we can get. For the red curve, this would be the best solution. So now we want both. We want speed and comfort of the car at the same time. Now the question is, what is an optimal solution, right? What I plot here is X. Of course, I cannot only plot two-dimensional, so we see as a one-dimensional decision space, and here we have F1 and F2. Cool. Question, is this an optimal solution? The answer is no, right? Because here is the value of F1, here is the value of F2, right? Which per se, well, is okay. But if we move here to the right, we see that the red curve as well as the blue curve decrease. Well, so that is that I will get a better car according to these two objectives if I am, for instance, here. So this is not an optimal solution. Is this an optimal solution? No, it's the same. It's symmetry argument, right? So if I now go to the left, right, I see I get better here and get better here, and I get another better car. So now we want to have something which is optimal. So this is optimality. This is an optimal point, because locally we know we only have two ways to go, locally left or right. Now I go left. If I go left, I see the red curve decreases, which is a good thing, but on the same side the blue curve increases, which is not what we wanted. I wanted to minimize all of them together. Now on the right, the good thing is blue goes down, but red goes up, right? So I cannot, if I compare this point with points in the neighborhood, I cannot say that this point is better than any other point according to the entire system, which means to all k objectives. So if there is nothing which is better, right, we have to call it a winner, right? So this is an optimal solution. Now, if you look at this, you don't see that this is only this guy, right? The same, well, here they intersect the curves, but that is absolutely not important, right? Here is the same thing. I go right, one goes down, one goes up, left, another thing happens. So we don't have to deal here with one solution. This here is a very typical thing, but we have an entire set of solutions, right? All these points here are optimal in the sense I just have explained, and we have to call them all winners. So all of them are of potential interest for our problem. This is the so-called Pareto set, now named after the inventor Vilfredo Pareto, more than 100 years ago. So this is the set of optimal solutions, the set of optimal cars. Now, there is the Pareto front, which is the image of the Pareto set. Here it was X against F. Here we see F1 against F2. Right? And in general would be against F3, F4, and so on, right? For every point here, I said there is a F1 value and an F2 value. Now I plot them exactly in this graph, right? It's F1 against F2, and if I map under F, right, the Pareto set, I get the Pareto front. So Pareto set and Pareto front approximations are very important, because these are, by our definition, the optimal solutions, right? So this is, of course, something which is a trouble. Now, I don't have one best car, I have a whole set of cars. And in the following, I would like to convince you that, well, I show you, you can follow me, that in general we can expect that the set PQ is the Pareto set, is in general a manifold of dimension k minus 1, which has a crucial impact on the decision making, right? What I said, multi and many objective mathematically is the same, but from the practical viewpoint, it is not the case. So we would like to prove or see evidence that the Pareto set has a dimension k minus 1, which I also need for my methods later on. Good. So for this we need optimality, Pareto optimality. First order condition is defined by first shown by Kuhn and Tucker in 1951, long time ago. And it says the following. Oh yes, I said I have to reduce today, and one reduction is that I do everything here for only unconstrained problems. So everything holds for constrained problems, but it's more complex, you know it. But it extends to the constrained case. But it just gives me the freedom to talk a bit less, right? Okay, X is Pareto optimal if there exists an alpha. Alpha is an RK, which we call the convex weight, and because it is a convex weight, sorry, that the alpha i's are all non-negative and they sum up to 1. So that makes it a convex weight, and such that the weighted sum of the gradients is 0. Or in other words, the 0 vector can be expressed as a convex combination of the gradients, right? So this is the first order condition of optimality after Karosh-Kuntaka and for multi-objective optimization problems. So that's all the first order, the second order thing. So we call them candidates, or we call them also Karosh-Kuntaka points. Makes sense, right? Two things I would like to tell. Alpha has a physical meaning, or geometric meaning, sorry. Here is the Pareto front. For x, I have here f from x, which is of course at the Pareto front, because I'm looking at optimal solutions. And one can show, I don't do this here, that alpha, this convex weight, is orthogonal to the linearization of the Pareto front. So this will be an effect which will be used later on for our algorithms. So again, alpha, the weight vector here, is orthogonal to the linearized Pareto front ff from x. Next thing, this here can be expressed here as J transposed alpha, where J is the Jacobian of f at x, right? This is just the gradients transposed, right? This is just the notation, right? Okay. Good. So we call them Karosh-Kuntaka points in the following. I'm interested in the detection of Karosh-Kuntaka points. As I said, I make here mathematical programming techniques. There is no global heuristics which I merge in so far. So we are transforming the problem of computing the optimal point to the first order conditions, right? So we transform this point basically into a zero set. That's what I'm doing in the next slide. Oh no, I wanted to show that the Pareto set is a manifold. Also, we need this later. And this was the transformation of the zero set. Now what I do is I look at this artificial auxiliary function f tilde, which maps from the Rn plus 8, because x and alpha goes in, and maps into the Rn plus 1. And f tilde from x and alpha is defined as the weighted sum of the gradients and the sum of the weights minus 1. Now, if we look at the theorem of Karosh-Kuntaka, which I just presented, we see that all Karosh-Kuntaka points are included in the zero set of f tilde. So we transform our optimization problem into a zero finding problem. And there are two results I would like to show. The first one, well, this is the transformation, zero finding thing. And then, well, if we use this, we use some smoothness assumptions on the FIs. Basically, we say the objectives have to be in conflict. Then we use the implicit function theorem and see that the Pareto set is of dimension k minus 1. Right? So I need a regular solution, and then the solution set is of dimension this minus this, which is this. Right? So in general, I expect the Pareto set, the set of optimal solutions, to be of dimension k minus 1. And that's, of course, a big thing. Right? In single objective optimization, one best car. Now, I would like to have to define the performance of the car by 2, 3, 4 different objectives, right? And well, at least I'm a German, all Germans love their cars, right? And for Germans, there are not 2 objectives, right? So for cars, there are 20 objectives. Or there is emission rate, not that important, right? There is speed, there is performance, there is sexiness, whatever, right? All these things, right? So we can easily extend it to much more. So you see already, like that's what happened. Like when I was like a PhD student, I was going to industry and convincing the people that multi-objective optimization is important. Now years later, not just by me, but by all the community, people are convinced, and decision-making problems are getting more and more complex. So also, it's a natural consequence that in the multi-objective problem, more objectives are being considered. But exactly this thing, this manifold thing, is the reason why we separate formally into multi and many-objective optimization problem. Now, what else we think? For instance, if we have a 2-objective problem, B-objective problem, we have here F1 against F2, we are able to compute the Pareto front. Of course, that's my job, right? So for now, I'm the algorithm designer, you're the decision maker, right? So I compute these things, maybe 200, 500 points, discretized, and that's this one. And then you would like to select, because at the end of the day, you don't want a manifold of cars, right? You want one car, the best car. Right? So, and I give you 2,000 solutions, and these 2,200, you don't buy them, right? You say, I want one, but now if you have this one, you can select, right? So you know what the difference of A and B is. We would like to minimize. B, for instance, if I go from B to A, I see F1, I gain something. But if I go from B to A and F2, I lose something. So if I have car B and I would like to go for car A, right? So the decision-making process is easy, right? I have this win and I have this sacrifice. That's fine. So I present you this set and you decide, right? In principle, it's the same if we have three objectives, right? That's the maximum I can plot. F1 against F2 against F3 Pareto sets look like this. Then you say, okay, here, here, here. And then you can do in principle the same, but of course, we all know that 3D plotting is getting tricky, right? So there is something which is not so easy, but it works. Now, 4, right? 4, well, I can only plot 3-dimensional. So what I can do is I can plot F1 against F2 against F3. I leave out F4. So I can put F1 against F2 against F4. I leave out F3, and so on. So I have here 4 different 3-dimensional projections, and you know this grows exponentially, right? So now if I have a point A, a point B here, right? For A I have 1 point here and 1 here, and 1 here and 1 here, 4 different points. Now for B is the same, so I have 8 different points, but grouped into 2. So we see already that the decision-making process maybe is possible, but it's not really good, right? So, and more than 4, I don't plot you anymore. I think you get the point. So if we have a car and we want to have the best car, we might have 15 objectives, right? I will show you an example with 14 objectives later on, right? Which really exist. We cannot say, well, this and this is the same. At least I cannot do it, right? So we have these problems. And the trouble is twofold, right? The first thing is I have to compute this. So this is not a manifold which says I'm this. It's never given explicitly. So I have to compute these things. And this is growing exponentially, right? So you can say, well, maybe I don't care. I don't want these manifolds. I say I take 3 points per coordinate direction, right? Or per dimension, right? But 3 to the power of 14, if you have a 14-dimensional problem, is already 1.6 million. Right? And that's growing, right? So this doesn't work. And you cannot say 2 or 1. I mean, 1 is ridiculous because then you get only 1 point, right? So this is the challenge for the algorithm designer. And the next thing is assume even I have 1.6 million or billion points. Then I give it to the car industry and to the manager and say, okay, here's the solution. So then the next question will be, and what the hell should I choose, right? So this is what we also had. I said, what the hell? I cannot do it. So that's why we will now, mathematically it's the same, we will formally divide into multi-objective optimization problem. There's maybe 2, 3, 4 objectives. Depends how tough you are. 5, I don't care, right? But if it's 14, 15, 20, which such problem exists, I would not call it a multi-objective problem anymore. So we divide here, we say this is a many-objective optimization. Mathematically the same, but they need different treatment. Here we can compute all. Here, maybe here we can compute all after this definition, but very, very soon, at 1, 2, 3 objectives more, you get lost, right? So today I would like to talk about the treatment of multi and many objective optimization. As I told you in our group, we have many of these algorithms, but today I would like to talk about continuation methods. And for our continuation methods, I need one technical detail, which is completely easy, but it will occur on and on, so I'll prove it, which is a ridiculous proof. You know all line search. You have a point, you have a direction, you step in this direction. Of course, the change in decision space is new, right? X new is x plus t times new. This is new, you change there. But we need the change in objective space. So if this F1 against F2, where do we change? And the answer, it is j times nu. J was the Jacobian, which was all the transposed of the individual gradients times nu. Nu was this here. So if we choose nu such that we make line search in this direction, the according direction in objective space is j times nu. Here is the proof, which is completely easy. This is just, if you look at the infinitesimal change in the ith objective, right? This is just this here, fi of x plus t times nu minus fi of x divided by t, and of course not for a fixed value of t. For t going to not infinity to 0, this is a mistake, right? Then we know from calculus that this is the directional derivative, and this is nothing else than the ith component of j times nu. So we are done. This is the proof. So again, if I move in direction nu, j times nu is the according direction in objective space, which we will need for our continuation methods. Okay. Before I come to the continuation methods, I have to admit that I'm not the only one dealing with this problem. There's a whole industry, even in academy, dealing with these things. You can roughly divide them in two. I did it here in 3 different classes. First of all, there are mathematical programming techniques. They're classical mathematical programming techniques, which you all know from school, adapted to the context of multi-objective optimization. I will dedicate one slide to this later on. And also the good thing of these methods is you can put in preference information. I told you before, nobody wants a manifold of cars. Well, nobody has the money of this, right? So you want one car, and if you want one car with this and this feature, why don't you put this into the mathematical programming technique? There are techniques for this, but I will tell you that they have to be handled with a lot of care, right? Then there are set-based methods, such as evolutionary algorithms, cell mapping techniques, subdivision techniques, which do not use one point, but an entire set of solutions, and evolve this set. That could be boxes, that could be individuals in a population, whatever. And the good thing is that they are of global nature, and the next thing is that they compute a finite size approximation, or an abstract approximation, in the case of subdivision, of the entire Pareto front or set in one single run, which is great. They are of global nature, but we all know global nature comes with a drawback, and this is the number of dimensions, right? You cannot say, hey, 1,000 dimensions, 10,000 dimensions, and it's global, and in 3 seconds. This doesn't work, right? And then by tactical reasons, I put continuation methods as a third category, which is kind of in between, right? It takes a lot of elements from mathematical programming, as I will show today, but it also has some heuristics inside, because what you can show is only completely local. Right? So you cannot show that you really reach the end point. Yeah? So they are in between because they're also in a way set-based, right? And about them, I would like to talk. But before I talk about them, I said, why not taking the classical methods? What we know since 50 or more years, there are, for instance, scalarization methods which transform the MOP into a single objective problem. What we can solve since many years. There is the weighted sum method, there is the absolute constraint method, there are reference point method, there are 20 different other famous methods and much more variants. And I will pick up one of them, but I will try to convince you that this, what I tell you, holds about all different problems. All of them have different advantages, but also have disadvantages. Now, look at reference point methods, right? So this is my example. What is the reference point method? I mean, you would like to have a car, right? And for your car, you have a certain idea. You want to spend this money for this performance, right? But the funny thing, or you are in a company and your boss wants this car with this performance, right? And you know your boss is always funny. I mean, this car with this performance doesn't exist, right? So you cannot have a car which has the same performance as the Porsche, but costs 20,000 pesos, right? So what can you do? I mean, there are 2 things you can do. You can go to your boss and say, oh, it doesn't work. That's one way, it's feasible, but it doesn't save your job, right? So the other way is that you do your best. That's also a very classical thing. You cannot produce this car. What you can say, hey boss, it doesn't exist. But what I can give you is the best. And what is the best? The best is that you minimize the distance of f from x, which is the performance of x, to the reference point z. The reference point is what you had in mind or what your boss had in mind. For instance, in this example, you see zeta, which is under the Pareto set front, and you will not get this guy because it doesn't exist, but you can get the nearest guy. So this is nice because this is something where you say, well, this is exactly what I wanted. What I wanted is I only want one car, and I need only to compute one car. Why should I compute another car, right? So I only want one car with this feature, and this is the best I can do. And I will not say that these methods are completely bad, because they were invented by great guys, right? But what I tell is that they're not always what you're looking for, in particular in many objective optimization. You should not trust this. The solution, big star of our problem star, right, depends on various things, right? It depends apparently on the reference point. If I change the reference point, the solution changes. You say, well, why should I care about this? Well, you should care about this because if it's a car, you have a good idea. But if you work in a space mission agency and your boss says, I want the trajectory designed from Earth to Mars, you don't have a very precise idea what the cost is, right? So you have no idea. And if you change, well, it costed 3 million pesos. Well, you get another answer than 30 million pesos. And I don't know what's better. I have no idea, right? So there are examples where you don't know this. The next thing, it changes on D, the distance function. And the distance function, I cannot go into detail, is a very, very delicate thing in multi-objective optimization. Basically, whenever you have chosen for a norm, you destroy the multi-objective problem, because it says objective F1 is as important as objective 2. So then, or twice, or 3 times, you have to put them in a relation. And if you put them in a relation, you destroy the multi-objective setting, right? And the next thing is you can ask your boss, you have a 23-dimensional problem, say, boss, what is your favorite norm in R23? Right, so this doesn't work. But okay, if you say, well, I don't care, I can solve these 2 things, but there is another thing, and the last thing is not in your hand, right? And this is that the whole thing, the solution Z star, depends also X star, depends on the shape of the Pareto front. And that was the idea. I do not want to compute the Pareto front. If I have the Pareto front, it's done, right? I don't want to compute 3,000 points to get 1 optimal point, right? So it depends on the shape of the Pareto front, period. Right? So we cannot do anything. And this is something where I say, well, X star is maybe not so bad, right? But it is not that X star should be the trusted one and say, this is the ultimate point. In particular, if we have more objectives, right, the whole thing gets more complicated, and we should see this maybe, and that's what I see, as a starting point, right? We see it as a good starting point, and if this works fine, well, if we are fine with it, it's good. If not, we maybe reiterate these things, if we need it, right? Okay, what I tell here holds for reference point methods. If you're familiar with reference point methods, you will realize I gave you the most simple reference point method, right? Which is even not a good one in many, many cases. But it was easier for me to explain, and my message is, or my opinion is, that this holds for all, also for the achievement scalarizing function, which is the top one. But even the top one has exactly these 3 things, right? Where you say, okay, you change something, you change the whole thing. And this is something where I say, no, X star is not the ultimate solution. That's my thing. So what can we do? Well, here advertising, I said, of course, we make our methods, right? We apply our methods. Well, we have different methods, and one of these methods are continuation methods. And before I come to my methods, I say what is classically done since the 1960s. These are predictor-corrector methods, and they work as follows. This is a nice slide, even if you're not interested in optimization. This is something you see on and on and on, applied to many applications. So predictor-corrector methods can be explained as follows. I have the following problem. H maps from the Rn plus k, here's n plus 1, into the Rn, and I define it as a zero finding problem. So attention, not Newton method, right? So it's not Rn to the Rn, so this is this guy. So then I have a solution. In the solution, so x0 such that h of x0 is 0, and that the rank is maximal, it's n. Right, so I have a regular solution, and then the PC methods can be described as follows. I know by the implicit function theorem, which is an existence theorem, that there exists a curve in a certain interval which maps into the Rn plus 1 such that c of 0 is x0, and here stop, and another message, h of c of s is 0. Right? So all these zeros set locally can be expressed by a curve. I told you implicit function theorem is an existence theorem. It doesn't help you that it exists, but it doesn't help now how and where it is. But here comes the trick, and this is a very nice trick. We take this guy here and differentiate it, right? If we differentiate it, we get h prime of c of s times inner derivative c prime of s is equal to 0. 0 derived by s is 0, right? So that's the point. And this here we said we have a regular solution, so this guy has a kernel one-dimensional, and we are looking here for a kernel vector. That's the great thing. So we have a one-dimensional thing. So we can, if we compute the kernel, we get the tangent vector. And that's what we do. We transform the zero finding problem now into an initial value problem. We have an initial value, x0, and at every point we don't know the curve, but we know c prime of the curve. We can compute it by looking at these kernel vectors, right? And there are, well, basically in literature there's only one way until we came to solve these things, and this is by a very classical trick from numerics. We take the QR factorization of h prime of x0 solely transposed. If we do this, we know that these guys span the range, and the last one is the kernel vector, right? That's what we wanted to have. Then we have to see the orientation. This is a trick I'll leave out, but then we can do it in two ways. We transformed the zero finding problem into an initial value problem, so we can even solve it. But the thing is that we can do it better. Typically, they do it in two steps. The first thing is they take the predictor. So they take this kernel vector and step for a certain while. So this is the Euler method maybe, right? And then we know that our problem was formulated as a zero finding problem. So we know that we have h of x is equal to 0. Now here we take the Newton method. Well, we take the Gauss-Newton method for this particular problem. I have some pictures for you. Here is the curve, the zero set of h. That's the curve. I have a starting point. What I did here, I can show on the pictures. We have this point. This here was the kernel vector, is a linearization of the set. We linearize this set, we go there for a certain stretch, knowing that we make a mistake, because the curve doesn't have to be linear, but could be curvy, right? So we are here, and then we know that we have this, we project. Then we are the same. Now it's an iteration, right? We move along, project, da. That's what we do. So this is the predictor corrector methods to trace these curves. So numerically, this curve is traced x0, x1, x2. Right? So that's what we have. Everything is fine in a very general sense. Already 2001, Hillermeyer came and had the state-of-the-art algorithm, and he said, well, now it looks very easy after all these slides. He said, hey, I take if tilde, which you can call h. It doesn't matter, right? He takes the Cauchy-Kontaker function, right? And if you look at the Cauchy-Kontaker function, it was actually exactly this. Rn plus, well, if k is 2 is 1. K doesn't matter. It's just for sake of easiness, into the Rn plus 1, and we want this thing. So everything is fine. So Hillermeyer did it, and this was the state of the algorithm for at least 15 years, right? So this was nice, but then one of my master students came and looked at this, and looked in particular at this function. This function is as follows. Here we have, this is x1 against x2, and this is a line. This is the Pareto set. So if the set of interest is a line, question, the continuation methods are good or not? Who thinks that continuation methods are good? I take this as a yes, and you're right, right? The thing is that if I have a line, then the predictor is already perfect. I don't need a correction step. So whenever I have something, object is a line, then continuation methods are perfect, because this two-step thing need only one step. And that second step, which is the hard step, Newton's method, gets deleted, right? So we have something which is great, but the thing is we're not living in X space, right? We're living in X alpha space, in the compound space. And here's x1, x2 against alpha 1. I cannot plot four-dimensional. But if I have alpha 1, I have alpha 2, because alpha 2 is 1 minus alpha 1. And we see this object is highly nonlinear. So that's the point. If we use the method of Hillermeyer, the classical method, right, we are in compound X alpha space, and the trouble is that the complexity increases. The nonlinearity of the problem increases, and this is something my master student wanted to reduce, and that was some years ago, and we led now to several different papers in this direction. Good. So the result is the Pareto tracer, and the idea is exactly to separate X and alpha space in the computation wherever possible. Of course, you cannot separate them. For every X, there is an alpha full stop, right? But you don't have to compute them directly. You would like to separate these guys, right? And this is exactly what we do. This is for the predictor step. For the corrector step, we adopted an existing method. Now, here I would like to show you in 3 technical slides, and then I have normal slides, how we have done it, which costed us a lot of headache, but the general idea is this guy here. So remember, we would like to have kernel vectors. Kernel vectors, we could take the transposed and the QR factorization, but then we are living in the X alpha space, or I call it mu space, right? So we would like to avoid this. So what we had, this here is the transposed of, no, it's not the transposed anymore, it's for QR transposition, sorry, this is the Jacobian of f. Derivative of f is this, and we need kernel vectors. That looks complicated. We look at this guy first. This is just the sum of the mu I is 0. If we have for now a mu that this is 0, then we can compute it, because then we can isolate mu. This, assuming to be regular, we put it on the other side. We have mu, which is still undefined. So if mu is given, we can solve it. Well, this is like a separation, so to speak. Question is how to separate things, how to choose mu. Well, here I have to say what we have done before. Remember that for a direction D in objective space, if I would like to shoot in a direction, this is nothing else than J times nu. So I say, this is an additional constraint, I shoot an objective space in a certain direction D, and D is nothing else than J times nu. That's what I would like to do. I say, I make a step in this direction. That's okay, we have a predictor-corrector. I want to go in this direction. So if I do this, I put this all together, doesn't matter, don't look for the details, I can solve it. Mu is given by D, and it's uniquely defined. So if you give me a D, I can give you a mu, and if we have a mu, we have the nu, right? So I can shoot in this direction. So I have separated these things. Question is how to choose D. Anybody an idea? We shoot along the printer front, right? That's what we do. Yeah, we have this, and we have this guy. Remember that what I said before, at f from x, alpha has the geometric property that is orthogonal to the linearized printer front. So it would be nice to shoot orthogonal to alpha. That means along. Orthogonal to the Pareto front is along the Pareto front, right? So that's easy. So we need all the vectors which are orthogonal to Pareto front. So what we do is we just do a QR factorization of alpha. So if we QR factorize alpha, Q1 is the first column vector is the span of alpha. So the other one forms, or the Q2 until Qk, an orthonormal basis of A transposed. That's where we shoot. And now we know where to shoot. Right? We know how to get the vector, and now we can state basically these main results. This is the main result for today. And if we have a Karush-Kontaka point, which is regular, and the gradients do not vanish, right? The rank has to be maximal, These and the H alpha is regular, so very standard assumption. Then, and that's the great thing, we can find an orthonormal basis both of the Pareto set and the Pareto front. And that's a novelty, because before it was in the compound X alpha space, and now we say, okay, Pareto set in X space is this, Pareto front is this. And this is the key for our algorithm. Now we can shoot along the Pareto front, and we don't increase the nonlinearity. Good. For the corrector, we use something from literature, one by one for the unconstrained case. For the constrained case, we modified it, but well, I don't talk about this today. So we have a complete predictor-corrector method. So now talking about cost, predictor-corrector method, all of them meet the Hessian. H alpha was the weighted sum of the Hessians, which is of course always a bad thing, and you should always think about approximating the Hessians. That's what we did here. And remember what we do here. This is the curve. What we do is we take small steps along and toward the curve. So everything is small. So also the Hessian changes by small amounts. So it's a very natural thing to use quasi-Newton methods for this. And this is the most effective algorithm of all we have, right? And maybe here's some results. For the unconstrained multi-objective problem, where this is the Pareto set and this is the object, nonlinear in X alpha space, right? The results are all the same. But the thing is, Hillermeyer, for instance, gets also this result, but he uses 65 functional relations, 216 Jacobians, and 432 Hessians. Hessian, remember, the growth in n is linear for the Jacobians and quadratic for the Hessians. So we have the Pareto tracer, which uses the Newton method, and the Pareto tracer, which uses the quasi-Newton method. So we have the same result using only 63 functional evolutions, which is comparable, and 63 Jacobian evolutions, and 0 Hessian evolutions. So we are much, much better. It's one order of magnitude better in the performance, while in the speed, right, in the cost. Where we can also treat equality constraint problems. Here you see a very nice result. This I always show when I talk in front of evolutionary algorithm guys. This is a 100-dimensional problem. We made it also 500-dimensional. This is an equality constraint. We get this result, which is a perfect result. And we need, for this, we need 192 function, 191 Jacobian evolutions. If you count that the Jacobian evolution is used by differential automatic differentiation, sorry, then we can count 4 times this. No, 4 times this is 1 times this. This is what you do with automatic differentiation. So we can count it back to function relation. So I get this result in a 100-dimensional problem, equality constraint, with less than 1,000 function evolutions. Yeah, do this with an evolutionary algorithm. I know the thing is unfair, but people always ask for comparisons, and that's it. If the Pareto front is disconnected, right, we will not find anything unless you give me 2 starting points, or all the starting points which are required. This is the local method, but a local method has to be efficiently locally, and I think we are the state of the art in this direction, right? We can also add other things. We can also do 3 objectives, right? This is a very nice approximation for 4,000 function and 2,500 Jacobian evolutions, so this is really state of the art. We maybe can even have 4, 5 objectives, but then we reach the limit, as I said. It's just a thing, structural thing in the problem. A multi-objective problem solution set is of dimension k minus 1. Right? So we cannot compute this, and for this we came up with another framework. We call it the Pareto Explorer, and this is done in 2 steps. The first one is that, look at the picture, we compute one solution, or a set of candidate solutions, 5, 10, and we pick out one out of them. Ideally with a global method, maybe with a reference point method, knowing that this is maybe a good starting point, but it's only a starting point. Yeah. Then we refine this solution having a path in user-specified directions, which I call D here, for instance. And that's exactly the thing. I mean, I need a direction, and the user say, well, I want to have more of F1, I want to have less of this, dada. And all these things can be done and realized efficiently by the Pareto tracer. So this is a new framework. We call it the Pareto Explorer, but it's basically 2 steps: global starting point. This exists, and then the application of the Pareto tracer. And this steering, as we will see later on, can be done in many different spaces, for instance in X space, in the objective space, in weight space, and in other things, right? So that's what we do. Well, these I leave out. For instance, in objective space. So you have this point, apparently you don't know the Pareto front, right? But you say, I would like to go in this direction. Well, this direction doesn't exist. Right? Unless you know the Pareto front, which you do not know. But what we can do is we can make, again, the best fit. So we have, due to our theorem, the linearized Pareto front in our hand, and then we have this direction. We want to shoot in this direction. We cannot. What we can do is we can make the best fit. It's always a QR factorization, right? That's what we can do. We can do the same in X space. For instance, I have this solution, X 100 units of x1, 1 and 2 units of x2 and 3, that's too much because this is a strange Earth and I don't trust my provider. I want to reduce it. Sure, from this point, this is the Pareto set, which I don't know. I go in this direction. Yeah, I can do this, but that's not optimal. So we can do it again optimal. We have the Pareto front, we move along, so that means we move here along, which is an easy task for 2 objectives, but for 20, it's not anymore, right? Okay, so we can do this, and then we can make different changes. This for time restrictions I have to leave out. We have 7 or 8 of them. So decision and objective space, you understand. This here, it doesn't matter. So last thing, there is an example. This is together with the industry. So it's a real-world application. I define real-world application if the industry pays for it, and Carnegie's are paid for it. Carnegie's is dealing with laundry systems, washing machines, but not one washing machine, huge areas, huge amounts of washing machines for laundry systems, right? And they have different objectives, right? I said, you know what, I would like to be, my washing should be good to reduce the wool grease type A, the wood in wool grease type B, and so on. Blood, starch, egg, all these things. So, when this is 13 things, then the last one is the cost. I mean, this I understand. They want to make it good, they want to make it cheap. So there are 14 different objectives. If you ask somebody from chemistry, they would maybe say, hey, motor oil and blood is the same. Well, I don't know. Well, they asked and it's not the same. So they said, these are the objectives. So this is a natural 14 objective problem, right? So, and here is the not so good news. I'm only allowed to present you a simplified model. And the simplified model is consisting only of 4 parameters. This is the temperature, the amount of the cleaner. But here you see, this is a simplification because the amount of the cleaner, you can change the cleaner, right? But this is what I can show. Washing time and the frequency of the rotating unit. Right, so we have here a natural 14 objective problem, and now we solved it with our Pareto Explorer, and then we have two different things, settings. One setting is the following. These are now hypothetical examples. So we look at the model, we said, okay, we start with a high quality solution, right? So this is really what washes out completely nice, but the thing is it also has a high cost. The cost, remember, what's the 14th objective. So now I say, what happens if we reduce the cost, right? So this comes an animation video to say, to reduce the cost. Let me just see. Initial is here, yes, okay. So first we have to understand how to visualize a 14 objective problem. This here is the so-called Pareto wheel, or Pareto wheel is the normal name for all of these things. So what we can do is, I cannot plot 14 dimensional, but what I can do is the following. I take here the circle I divide into 14 parts, and every of these parts is supposed to be the value of an objective. And every objective value, I can put a certain range, from very bad to very good, right? So here, for instance, this here, the initial value is the black one, is the starting point. So this is all perfect, and this is all bad. So what we have is that quality 1, the quality indicator 1 is perfect, 2, 3, 4 is perfect, 9, 10 maybe not, but that is what Pareto said. You cannot have all, right? Everything is fine unless the cost. The cost is high, and that's not good, right? We want to minimize the cost. So we have here a high performance, high cost solution. So I would like to minimize F14, and we have used the Pareto Explorer for this. And let me see. Yes, we see this. We see that the cost changes, right? This is from bad to good. Well, and then the others change also. For instance, F1 was here and gets worse. F3, by whatever reason, doesn't change at all. The same for F6 and F8, right? F12 goes down like crazy, and that's it, right? So the thing is that I cannot show you the Pareto front. That would be 13 dimensional if I have the big model, right? So I cannot do this. So we have to do for something else. So what we did is we looked at a starting point, and here is the same. The ring here is the same, but in X space. So what we do is we look what happens. So this can be now done in an interactive way. The Pareto Explorer is my joystick. Well, joystick, sorry, I'm from the 80s, right? So it's a controller, right? So you have the controller, and you say, I would like to move along. So you move along, virtually, along the Pareto set and front, right? So you have a local Pareto front and set approximation, exploration. So this is what happens. I will not tell that before was better, after was better. For this is our tool which we give to the expert, right? And the expert should decide. I said, no, you know what, I want this better. Well, do it. We can do all these things. We have a MATLAB software which we also sell. Right, okay, good. So that's the one. Now this was okay for Carnegie, so they said, yeah, this is something we like, but this is very complex. We looked at another one, and the other one was really great, right? This was fine. My student came and said, well, this is a boring video. I said, I'll show you the boring video because it's the best video I have. So here we have again a high quality solution, but it has a large washing time. Washing time was X3. And washing time apparently is something which is important, because if you have less washing time, you can wash more, right, in the same time. So what we have this here, we said, okay, X3 should be minimized, so we have nu is minus X3, right? So now we run the video. And the video here in objective space is this. It's a video, actually. You see changes? No, I see changes because I'm nearer, right? But I see changes here. X3 has a change, right? X3 changes from here to here, right? And that is the thing. X3 was before 1.45. X3 afterwards is 1.73, which is basically 50%. Now, in objective space, that's what my student said, it's a boring video, but I'm proud of this boring video, because nothing changes. Of course it changes, this is what Pareto said. If you go along the Pareto front, something has to change, but it never says to which amount it has to change, right? So here it changes just for a little bit, so maybe this is curry, I cannot remember. If you have 90% of curry, which you can wash away, and then you have 89.95%, well, that's something. For me, it's basically the same. But washing time 50% less, this is something I can sell, and this is what we were selling. Basically, after this video, they were convinced, and they were paying, actually, for this project. Right? So I would like to say that well, this I think is a nice application to show our thing. The thing is that for multi-objective problems, right, you can compute everything. For many objective, you cannot. You cannot say what is all. Well, it's just not possible. So we have this new framework which says, from a starting point, go in the direction which you want. We have 7 or 8 different directions. We have learned today X and Y space, right, to say if you want this is the most natural one. You go in this direction. Right? So this is what we can do, but all of our methods are local. So conclude very shortly. There are 2 tools. I hope I have convinced you. If you have a continuous problem and you are fine with local methods, the Pareto tracer is fine. For multi-objective problems, the Pareto Explorer is hopefully also nice for many objective problems. And that's a nice thing. We started with this, but there's much more to do. Everything is local, so we would like to have it global, of course, so nobody asks for the best local solution, they ask for the best solution. But if you use the gradient, there is nothing to do, right? It's a local paradigm, right? So what we do now is we hybridize it with evolutionary algorithms or with other continuation-like methods. And another thing is that also the industry has asked for high-dimensional linear problems. So if you take something huge and you do it as good as possible, something linear comes out. So here, hybridization application to the Pareto tracer and explorer to linear problems would be nice, but it is not done. Okay, so basically I'm done with my presentation. I'm happy that I survived it. And one very last thing, this is some advertising. I told you that my group is called NEO, which stands for Numerical and Evolutionary Optimization. This is something we always have to make advertising for because either there is this community or this community. But if you want to solve the problem, it makes sense to take parts from here and there. And this is numerical and evolutionary optimization. And I had a lot of troubles to get things published and all these things. But I've seen the same for others. So I thought it would be nice to start with a platform. And the platform is the event series, is a workshop series since 2013. We have it every year. This year will be at end of September 26 to 28 in the Historical Center of Mexico City. Here you will see some information if you want to go there. Of course, ask your supervisor for funding and you can go there. Okay, that's all from my side. Thank you and open for questions. Por eso en español. No voy a entender, pero ella va a explicar. Traducir.
Pues muchísimas gracias.
Gracias.